You know, today is the 17th of March. It is St. Patrick's Day. Can you hear me? I guess I can't.
Yes, we're
All
good.
right, good. So, so there's two icons up here. One is for St. Patrick's Day, but I like the fact that this is also Evacuation Day, celebrating the day that after George Washington had fortified Dorchester Heights with cannon brought from Fort Ticonderoga, the British were forced to evacuate Boston. That would have been, what is it, March 17th of 1776. But that's not what I'm going to talk about today. And I give you the green border in honor of two things: the fact that it's St. Patrick's Day and the fact that I'm going to talk a little bit about the greenhouse effect. And here's what I am going to talk about. But before that, I just want to give a few prefatory remarks. This talk is inspired in part by John Rudy saying, you know, if somebody would like to talk about something they don't know anything about, this would be a chance for them to learn something about it. So that was one.
Hooray!
And the other inspiration, another inspiration was Shelley Lowenthal's talk when he was talking about climate science. And I thought, having listened to that talk, it would be good to know more. And then a third sort of follow-on inspiration was I decided if I were going to talk about the greenhouse effect, it would probably be good to understand some of the issues in climate science. And then I got another suggestion from John Rudy a long time ago that it might be more fun to study online courses as a group than by yourself. So it inspired 5 of us to get together: Carl Lazarus and Mike Alexander and Jerry Slate. And for a while, Harry Forstick and I were a study group going through the Penn State Earth Sciences course called Earth's Future, Climate and Future. That was a very interesting thing to do and a lot of fun. I mean, those were good guys to share this with. Anyway, I went through that partly because I wanted to learn about the greenhouse effect, but in fact, there was not that much about it. So I had to spend some more time doing other things, learning about the greenhouse effect. Well, here's what I'm going to tell you about today. I'm going to talk about Venus mainly. Actually, I'm going to talk about Venus and compare it to the Earth. That's the first thing to do. Talk a little bit about how the energy flows from the sun into Venus and into the Earth. Talk about how energy flows out in infrared radiation from the Earth and Venus. They both do this. And then, because you can see, we're talking about solar and infrared radiations. We're talking about electromagnetic radiations. We're talking about light, infrared, and other forms of electromagnetic radiation. And so I'm going to talk something about black body radiation and properties of radiation and its relationship to temperature. And then we get to what's fairly important, the effects of atmosphere, which are in some sense simple as a shield, as a heat transporter, but, and this is where we get to the greenhouse effect finally, how an atmosphere traps heat and warms a planet's surface, and what the mechanism is for that kind of trapping, and what happens if you add more. We'll talk mainly about CO2 because that's always the one that people are most concerned about. So we're going to talk about Venus and Earth, and we start out talking about some of the properties of Venus. And one of the notable features historically has been of interest is that Venus and Earth are very similar in many respects. They are both fairly close to the sun. The Earth is 1 astronomical unit, that is 1 Earth distance from the sun, and Venus is 0.72 astronomical units from the sun, so it's closer. This picture is actually taken from an article in which people are talking about the habitable zone around a star because they're interested in that as they're talking about exoplanets. and they want to be able to characterize which exoplanets are likely to have water. And water is the decisive element or decisive molecule, if you like, for habitability by given our parochial knowledge of life. And so the shaded area is the habitable zone around our sun by somebody's criteria. And you see, Venus is not quite in it. Earth is in it and Mars is in it. And as a result, we find Earth looking like a blue marble. And we find Venus, we don't actually see Venus looking as desertified as this, but before I go there, I want to show you this because it's a pretty picture. This is a digression, really. But this is a different view of the inner solar system. You can see Earth is there, and then not very far away from it in the purple line, that's where Venus is. Mars is out here in the red. And I guess people define the inner part of the solar system as out to Jupiter's orbit. But the thing I thought interesting about this picture is every one of these little yellow dots is an identified meteoroid. So and every one of these little white arrowheads is a comet that's a known comet. And they're all pointing in towards the sun because comets come in like that in these almost parabolic orbits.
Do you want to take a moment to define the difference
between a comet and a meteorite?
Yes. Both
I would say
what they're made up of and what their path is.
Oh, probably no. I'll tell you the path difference. There's a lot of variation in what they're made of. I mean, the meteorites tend to be stony. The comets tend to have ice on them and stuff like that. But mainly the orbits of the comets are extremely elliptical, with rather large, usually with large periods. Whereas the meteorites are going in more or less circular orbits. You know, this is the asteroid belt. So we're talking about asteroids here. Every one of the yellow dots is an asteroid.
So what's the difference between an asteroid and a meteoroid?
I don't, I think asteroid begins with an AST and meteoroid
okay.
begins with an ET. Right.
I think that asteroid is like a planet-like object that goes around the sun in an orbit. When it falls to the Earth and it hits the atmosphere, it becomes a meteor. And when it hits the ground, it becomes a meteorite.
Yeah, but a meteoroid, you see, is what it is before it does any of those things, I think. All right. All right, so I put this in just so we could get questions like that. And incidentally, I love getting interrupted with questions, so don't hesitate. So what we're going to talk about here, just a little comparison between Earth, which I have characterized here for your interest as a very nice place to live. And we're going to contrast that with Venus, which is here seen in visible light from about 12,000 kilometers out. Now, we've been looking at Venus from Earth with sort of modern look at Venus in our age of exploration. You know, I think it is an amazing age of exploration. And we have sent 42 missions and counting to Venus. When I say we, I mean the Russians, the Soviets actually started and did the earliest numerous missions. The Americans have done many missions. I think we're probably now the leader. The Japanese have sent missions. The European Space Agency has sent missions. And so we're all very interested in Venus. And we'll look at some of the distinctions between Venus. Let's see, is that right? Yeah, I guess I don't know why there's a blank slide in there. One of the things we see here is the earliest pictures that came back from Venus were rather disappointing, at least to me as a teenage aficionado of science fiction, where Venus was usually depicted as this luxuriant forest of tropical jungles and dangerous fungi, you know, and things like that. It comes back looking like this rather stony, dark, plate-like rocks beat up. I mean, we're not seeing very much of Venus when we see this, and we're seeing like this object is a lens cap from the lander. But it took 13 tries. This is Venera 13, the Soviet lander. Took 13 tries before they could get a color picture. Took 7 tries before they could get a black and white picture. This is not the black and white picture from the 7th try. This is just taking the color image as it came back from Venus and turning it into what it would look like if we were seeing it by our quality of sunlight. So if you took a slab of Venus and brought it to Earth and set it down and looked at it, it would look like this. If you're on Venus itself, it's going to look like this. And this kind of yellowish tinge is ominous for a reason which we can talk about next. Venus is colored by sulfuric acid clouds, and the light getting down to the surface of Venus tends to be kind of pukey yellow, as I'm given to understand. And there's how it looks by sunlight. You know, things on Earth actually look better to me, but then that's, again, the kind of parochialism that we know exists. And so here from Venera 14, 2 pictures. And one of the things that took so long, one of the reasons they had so many failures was they did not understand that the atmosphere on Venus is about 90 to 94 times the density of Earth's atmosphere. And that as a result, you would send in first early probes and they would go down through the atmosphere, and somewhere around 27 atmospheres, well above the surface, they would be crushed by the atmosphere. This is like, I mean, 94 atmospheres, it's like going to 9,400 meters, going to 940 meters of water. So, you know, that's almost 3,000 feet. And that's a very serious kind of pressure indeed. And as they learned it, there was more pressure than anybody had imagined in the atmosphere. They built stronger and stronger probes until finally what you're sending into Venus is very much like a diving bell. You know, it's encapsulated and it goes in. And finally, you get to, and then when you get to the surface, you find out that the temperature is 470, 465 degrees centigrade, you know, and that's hot enough to melt lead. And so not only do you have to protect against this incredible pressure, you have to design electronics and protect them and cameras and whatever it is so that it can live long enough to take some kind of information, take some kind of picture, and send it usually back to a relay satellite that's going in orbit around Venus. So it was a pretty tough job, but by the time they got to Venera 14, they could do it. The thing would go down, as I said, like a diving bell, and then it had a planned lifetime of 32 minutes. So you're sending your package there, your probe to Venus to learn about Venus. 32 minutes is what you're going to get for your money. Well, anyway, you can strike it lucky, and it can last, in this case, 57 minutes, which may be a record so far. You don't know, it might have lasted longer, but it's really satellite passed out of range after 57 minutes. And by the time it came back again, the probe was dead. So that's a Russian effort. I mean, I think they went up to 17 Veneras, and then there were 2 more. So they did 19 attempts at probes, and that's how we learned about the sulfuric acid, and we learned about we learned that the atmosphere is 95.6% carbon dioxide, but amazingly dense, far denser than Earth. So this is my little slide here of comparison of properties of Venus and Earth. Here's the ones that are similar, quite similar. The size of Venus, the girth, the circumference, 38 million meters. Earth is 40 million meters. You can figure out the diameter, 12,730 for Earth kilometers, 12,100 for Venus. The masses are not that different, and that's not surprising because the densities are not that different. So if they're going to be the same size and have the same density, they're going to have the same mass. And the surface gravity is not that much different. But, and the distance from the sun, is somewhat different, but here's where some differences begin to appear. First of all, the year is 223 days. Well, that's determined by classical mechanics. I mean, once you know that it's 0.72 out from the astronomical units out from the sun, you know its period is going to be 222 days. The solar irradiance, of course, is going to be up because it's much closer. So we get about 1,300 watts per meter squared. The Venus gets almost twice that because they're close. And a notable difference, though, is the albedo. That is the fancy word for the fraction of the incident radiation that's reflected. We reflect about 30% of what strikes the Earth. Venus reflects 80% of what leaves the Earth. As a result, you're only going to get about 20% of this solar irradiance going down to the surface. So that's quite a small number. Here's the big difference, and that is the tilt. Now, we get a tilt of 23.5 degrees, and that's what makes our seasons. You understand that? We're just coming up to the point where the sun will be directly overhead the equator, and insolation will be coming straight in. The tilt here is said to be 177.3, or another way to say that is it's 2.7 tilted to the axis, but 177.3. There's a kind of rule of how you measure the tilt. You use your right hand, you curl it in the direction of the rotation of the planet, and then you look at how much the angle of your thumb differs from the vertical. Well, 177.3 means you have to turn your hand over. And that means, and it's correct, that Venus is counter-rotating. It's rotating in a direction opposite to anything else in the solar system, which is quite interesting and merits some explanation. And people are still trying to explain it. There are some arguments, but I'm not going to go into that. But one of the consequences, another strange feature, is that it's not rotating very fast. Whereas we go one complete rotation in a day, Venus takes 243 days to make a complete rotation. And you see, its daily rotation is longer than its year. So it goes around the sun once and it still hasn't completed a rotation on its axis. All right, kind of different. But here's where the real differences are, and I've already mentioned them. The atmospheric pressure of Venus is 90 times that of Earth. Mars, for example, has a atmospheric pressure that is 1/160th of that of Earth. So we're seeing three very different atmospheres in these inner planets. The atmosphere's gases are 95.6% CO2, 3.4% nitrogen, and then there are traces. There may be some traces of water vapor up there. People aren't altogether sure. Whereas our gases, 78% nitrogen, 20% oxygen, 0.04% CO2, hardly any CO2 at all. And as I say, maybe traces of water, but so far as we can tell, there's no water on the surface of Venus or associated with Venus. And that has some interesting consequences because water on the Earth actually lubricates the tectonic plate movements. And so on Earth, you're going to have, the plates, they kind of jerk around, we get earthquakes, things are stutter, stop, stutter, stop. On Venus, what seems to happen is these internal stresses will build up, and there is no tectonic plate movement to release them until suddenly there is a cataclysmic era of volcanic eruptions. That's what people think from what they have seen of the topography of Venus. That's kind of speculative, but we're thinking about it. And then the real difference, the one that really stings, is that, and it means that going to work in the tropical jungles of Venus is probably not one of my options. is that the surface temperature is 470 degrees Celsius, 743 kelvins. I like kelvins, and I'm going to do a lot more kelvins than Celsius. And you have to do that. So we're at 15 degrees Celsius on Earth. That's kind of the average temperature. And a lot of the things I'm talking about are averages. And maybe at the end we can talk a little bit about why averages don't tell you everything you need to know.
Charlie,
Yes, George, what?
being that the day is so long, what does the temperature mean? Is that a day temperature or night temperature?
Well, I assume, I can't tell you for sure, George, but I assume it's done as we do it on Earth. Where that 15 degrees is an average over day and night. I suspect that the temperature is not wildly different at night on Venus because there is atmospheric circulation and there are sizable movements. But in any case, the answer is you take measurements, you put a grid over your planet, you measure the temperature in each square of the grid, and then you average those together to get your overall average temperature. And so if you do that for Venus, you'll pick up the night side as well as the day side, even though it may be that the day side is considerably hotter than the night side.
Charlie,
Yeah, go ahead.
you were commenting on the slow rotation of Venus.
Yeah.
That's like Mercury.
I don't know. Oh, Mercury does not rotate at all. Mercury is
Oh, it does rotate. It does rotate a little bit. That was
well. I think it's locked. It's locked to face the sun, the way the moon rotates a little bit and is locked to face the Earth.
Yeah, but do you think? Yeah, but is there something common between Venus and Mercury in that regard?
No, I think. What do I think? The speculation is that there are certain resonances between the Earth and Venus that may sort of drag Venus into the long day but as I said earlier, I don't think anybody has a really persuasive explanation yet as to why that should have happened.
Charlie,
Yeah, Peter.
since Mike brought up the moon, it was really part of my question too. Can you explain to an ignorant person like me the relationship between the rotation of the moon and the rotation of Venus? Are they the same? They different in terms of their effects and what have you?
We're talking about the rotation of the moon relative to the Earth, which is why it always keeps a face towards the Earth. So what I said earlier, that something similar like that is true for Mercury with respect to the sun. Mercury rotates so that it pretty much keeps one face towards the sun. And the tidal forces and the gravitational forces can be calculated and shown to produce this effect. Now, Venus is not behaving like either of those things quite. And so I don't know. And I'm not sure anybody really understands. I mean, there are people, someone once said of astrophysicists, they are always certain and often wrong. And so that may be the case for the analyses of Venus rotation period. But yeah.
I thought you said something about when the probes went into Venus that they went through sulfuric acid. Is there sulfuric acid in the atmosphere of Venus?
There are traces of sulfuric acid. Well, we've come to that point. Thank you, Dick. I want to just mention that now. So I said that the albedo of Venus is extraordinarily high. In other words, 80% of its incoming solar energy is reflected away. And in a way, you know that because you look out at night and what's the brightest object in the sky? It's Venus shining by reflected sunlight. And that is because Venus is wrapped in a cloud cover, a cloud cover that is pretty much opaque to visible light. And those clouds seem to be sulfuric acid, H2SO4 droplets. Rather unpleasant, you think. But in fact, the amount of H2SO4 in the atmosphere is kind of a trace amount. I suppose it might be comparable to the amount of water that's in our atmosphere. Well, I doubt if it's even that much. But as we have very small amounts of water in our atmosphere, still we produce cloud cover with those water droplets. So the atmosphere is mostly not H2SO4, but there is enough of it so that it can form droplets. And in fact, I'll show you later, there has to be a sulfuric acid rain on Venus that interestingly will fall, but will not actually reach the surface. Different story. Okay, so here, I wanted to, I'm in danger of using up all my time talking about Venus, but that's okay. But here I'm going to talk about Akatsuki. Now,
Excuse me a second, Charlie.
Yeah.
I wouldn't worry about the time. Why don't you just go ahead, handle the questions as they come.
Okay.
If we run out of time, then we'll put in a second session.
All right, John. Thank you. Anyway, I do want to tell you a little story about Akatsuki. Now, here, first of all, I'll tell you, Akatsuki is mapping the cloud cover of Venus. And that cloud cover is not penetrable by visible light, but it is penetrable by infrared. And so infrared will come up from Venus through it. And Akatsuki carries an infrared camera. And so Akatsuki can look in at the atmosphere and see, you can see all the structure in here. These are clouds, the cloud structure. They're showing you that there's weather of a certain kind on Venus. And the IR enables you to see down to about, say, 50 kilometers above the surface. This is the night side of Venus being viewed in the infrared at about 2 microns. Actually has two cameras, the camera has two beams that it can analyze. Very, very clever. And Akatsuki also can look at UV, so it can look at the clouds in the ultraviolet. And now it sees a different altitude of the clouds. You can see the clouds at about 70 kilometers. And you can see, if you know what to do, traces of water vapor in it. So you're looking at 365 nanometers, 285 nanometers. This is in the ultraviolet of our spectrum. But the real thing I want to tell you about Akatsuki is this amazing story. And if you've heard it, Akatsuki is a Japanese mission to Venus, launched in 2010. And it was supposed to go into orbit around Venus. And so as it approached Venus, it turned on its rocket motors to slow it down so that it would go into orbit. And the rocket motor failed. And so it did not go into orbit. There was a new ceramic, it cracked in the engine liner, and it went on, in fact, in its original orbit, which took it into orbit around the sun. The Japanese engineers dumped its fuel load so that it became considerably lighter. They waited 5 years for the thing to make 5 orbits of the sun and come back to where, by firing the attitude thrusters, the small rockets that oriented the thing, by firing those attitude rockets for 20 minutes, they were able to insert it into a Venus orbit. And since then, take all these pictures. I just thought this was brilliant and a wonderful story, and just waiting 5 years to see if you could do it. I mean, think of the suspense. Jesus. I think I'd get ulcers if I had to wait 1 day, but these are tough people. Anyway, that's part of the thing. And so the Akatsuki is, I think, still returning data. Other kind of ingenious aspects of probing Venus. One of the things that the European Space Agency, ESA, I guess they call themselves, has done is they've put something called the Venus Express into a very elliptical orbit around Venus, and then they use an instrument called, I don't know, they call it Soir or SOIR. Anyway, it stands for solar occultation infrared. And you see what happens is as it goes around here, going to go into the dark side of Venus, it actually gets to look through the shell of atmosphere that is around Venus, and so it can study that atmosphere, and it has been up there doing that for quite a while. And so one of the things they get from this is a map of the temperature of the atmosphere of Venus as a function of altitude. And it's down to about 75 kilometers. So they're looking all the way up to 160 kilometers. And they're seeing a temperature that is, kind of Earth-like, not bad, sort of 300 Kelvin. Then it gets very cold, and then it gets very warm again, and then it gets cooler, and then it starts down towards what's probably going to be the temperature, which is 700 Kelvin when it gets down all the way to the bottom. A curve like this exists also for Earth's atmosphere, and I'll show you one later. But this is just to show you how we get some structural information about Venus's, or we get information about the structure of Venus's atmosphere. It's quite an achievement, I think. All right. So the other thing is, I said that this cloud of sulfuric acid droplets that is so brilliantly reflected and so opaque to visible light, I said, makes it impossible to see the topography down below. And so what we have done, the United States has done, is send called the Magellan mission, and using this synthetic aperture radar to map, because you can use radar penetrates the clouds with no problem. And so with radar, you can actually get a fairly detailed map. In fact, that first ball that I showed you, the big desert ball of Venus at the beginning, that was all obtained using Magellan. And here is a kind of scan showing big craters down at the bottom. There's one there, and I think there's another one over here. So there's been a lot of activity. It's this kind of data that lead people to speculate that Venus has had these periodic cataclysmic eras of volcanism to release the stress in its crust. But one picture can feed a lot of speculation, but it's fun to do. So here, just again to fix in our minds, the big differences between Earth and Venus are the compositions of their atmosphere, as well as the pressure. 90 bars, 1 bar, 96% CO2, some nitrogen, very little SO2, which would feed the H2SO4. Probably comes from the breakup of H2SO4 by UV acting on the upper part of the atmosphere. Here's Earth.
Charlie?
Yeah, George.
The craters, are they internal? I mean, like a volcano, or are they from?
I take it from what I read. It's a good question. I take it from what I read that they're thought to be internal.
Okay, it's
But
not coming.
there ought to be some there too from external. Except that if there's if there are these periods of volcanism, they're going to erase craters produced from space.
Charlie?
And then the question is, how often do they occur? I don't know that. Yeah, Steve.
Charlie, the slide does say impact craters, and they have an appearance of impact.
So I must have thought at one time it was impact craters.
Okay, okay. They have an appearance of where if something hits
Yeah,
the stuff that comes out, and then they have the point in the middle, which would be of an impact crater appearance, wouldn't it?
yeah, it's like the milk droplets that you see when they drop.
Yeah.
Down and come back up and yeah, or drop into a liquid. So yeah, okay. Still, uh, okay. I'll just go on.
How does something get through that thick atmosphere without burning up?
It can be very big.
It would have to be very big,
Yeah.
Like-
I mean,
like so big it would be. If it's something like that hitting the Earth, it would be
I don't know.
massive.
Well, those are pretty big craters. But it's a good question, Jerry. That's why I was, what I may be offering is an indecision in the people who study this in detail. You know, that some may be opting for internal and some for external. But obviously, what Steve says is right. The source I was looking at must have said impact, and I wrote impact.
There are large craters on Earth. If you look up the Eye of Quebec, north of Quebec, it's a crater that's the size of Rhode Island.
Yeah, but this is, Jerry's point is if you're very big and you're coming down through that much atmosphere, aren't you more apt to burn up than something coming down through Earth's atmosphere?
Right.
It's almost 100 atmospheres.
Oh, that's true. Yeah.
Yeah. So
Well,
yeah.
if it's large enough, if the moon was flying into Venus, okay, it's unlikely that the whole thing would vaporize before it hit the planet. So I'm not saying that would happen, but that's how something could get through the atmosphere. It'd have to be considerably larger than it would be if it hit the planet Earth. The question I wanted to ask you, Charlie, is do we have any measure as to how big the diameter of do we have any measurements on the size of those craters? Because I've seen pictures that look like something massive, and then you realize that somebody's holding a picture of something a foot away.
Yeah, they put a marble into a sand pit or something.
Yeah, the kind of thing. Do you have any idea what the measure is on those?
I do not. I mean, I'm sure they can get that information from their pictures, but I don't know it.
I've also heard that the theory is that the moon was created when something similar in size to a planet hit the Earth and then created the debris that turned into the moon.
Yes, I think that's, there's been a long sequence of theories of how the moon formed, and I think that is the most popular current one.
The people who live on the moon say the Earth is the debris.
There we go. Charlie, looking at the chart that you have up here now,
Yeah.
is there any description or understanding of why we're surrounded by two planets whose atmosphere is primarily CO2 and we're nitrogen?
I don't know it, Peter. The O2,
We're just catching up with them.
the fact that we have O2 is strictly a consequence of there being life on the planet. O2 is not going to be found in any substantial amount on a planet that does not have life, because it's very reactive, chemically reactive, and will end up in the rocks. So that is a signature. I think we had a lecture by Sarah Seeger a few months back, in which she was talking about looking for phosphine, I think it was, pH4 on Venus, thinking they found it, saying that if it is there, it can only be there because it's produced by life. And that's why they were all excited about it. Well, that is certainly true of free oxygen. You do not have free oxygen anywhere unless there's life. So,
Well, Charles, the other thing is that both Venus and Mars are not famous for having had a great deal of plant life, which takes the CO2 and breaks it down to oxygen eventually. So, and sequester. Yeah.
I think we're saying the same thing, Tony.
Yeah. Okay.
There's no life there. There's no life there. There's life here, and that's my little picture of the dead-looking strip of Venus, and then underneath a shot of my.
You have to be careful. We have to say life. When we mean life as we know it.
You're right. Right. I don't think I want to meet life as I don't know it, but that may be.
Could be better, you don't know.
If it's anything like us, I surely don't want to meet it.
You know, another factor that would affect Mars is the fact that it's a much lighter planet, and there can be much more evaporation from its surface.
Yeah. Well, that's why we think there's no water on Venus or Mars, or or much less water on Mars, and practically no water on Venus, because we think the upper atmosphere, the UV, breaks up the H2O into H2 and some traces of oxygen, and then the H2 has escape velocity, and it's gone. All right. So I want to talk now about heat exchange. And so I'll go back to rudiments. I apologize to those of you who know these rudiments, but I think it's important to get them. Let's see why there. So, we are interested in global warming. We're interested in how the planets reach their surface temperatures. And those that has to do with a balance between the energy that flows in from the sun and the energy that flows out from the planet. There are only three ways to do that. We're talking about heat, and we use heat. I was kind of delighted by, I think it was Dan Klepner's nice account of Rumford and some of the other things that we heard about, but talking about phlogiston. Phlogiston is this outmoded cast aside theory that there's something inside matter that when you grind the matter, you release the phlogiston and that flows out. We actually still use the theory. We just don't use the word. It's people talk about it the same way as they talked about it back in the 18th century. But it isn't. I mean, real heat is molecular motion. It's the kinetic energy of molecules. If you want to heat something, you want to make it hotter, you make its molecules move faster. And temperature is just a measure of the kinetic energy of the molecules and how, half mv squared per molecule. But now if you want to transfer the heat, how do you do that? Well, you can do it, as it says here, by conduction, direct contact, in which the moving molecules vibrating in a solid vibrate against, say, your hand. And you say, oh my God, that's hot, because those molecules are bumping and making the molecules in your hand move. That's conduction, or down a wire, or anything like that. The one we know most is convection, because energy is transferred by actually moving the moving molecules. You carry the jiggling molecules from here over to here and back over to here, and you've transferred heat around there. So that's your convection. And of course, we know that because we see heat rise all the time, and that's very good. The one that's surprising and I think amazingly lovely is the radiation. And you sit with your hands in front of a fire or a electric coil or something like that, and you feel the heat coming. And that heat is actually electromagnetic radiation in the infrared. It's that's coming over to you. And so you notice these two really require the transfer of matter from one place to another, or at least the adjacency of matter. You can't do that in space for the most part. I mean, there are some things that happen. There's some matter moving around in space, but there just isn't very much. And so the only way you're going to move energy in any amount from one place in space to another place in space is by electromagnetic radiation. And that means we have to understand something about electromagnetic radiation. So in space, radiation is the main way to transfer energy. Earth is heated by radiation from the sun. Earth is cooled by radiating into space. Venus, the same. Radiation comes from the sun. Radiation comes in from space. There are some small effects of the fact that the Earth is compressing gravitationally. There's some little radioactivity in the Earth, and there's some energy there, but it's really not much compared to what comes in from the sun. And it's not much compared to what the Earth has to get rid of if it's going to stay at a constant temperature. Same is true here. So here's the really important idea. Sort of this curve is the important idea. This curve is the so-called black body radiation distribution, in which it's telling us how much energy per square meter is coming from an object that has a temperature. And I'll just lie for a minute and tell the truth more after a little bit. So let's say a body at a given temperature will have a distribution of radiations as a function of frequency. So it'll have some low frequency stuff coming out. It'll have some high frequency stuff coming out. It'll have a lot of something in the middle. And that's what this curve is telling you. The curve tells you sort of how much energy is coming out in electromagnetic radiation over some small frequency range. That is, if you sort of run a little vertical bar up and down in here, that would tell you so much energy is coming out between this frequency and that frequency. Now, I'm not using frequency units, and this is a real pain in the butt. The whole system is that, because you will often see the black body curve plotted as a function of wavelength. And I don't like to do that, because I like to do it as a function of frequency, because then the energy progresses very nicely linearly from left to right. High energy stuff is out here, low energy stuff is here. On the other hand, people don't like to use frequency either, partly for historical reasons, partly because it makes some very large numbers to go on your graph. And so they use something called the wave number. And the wave number is actually the frequency divided by the speed of light, which is also the same thing as 1 over the wavelength. So these are reciprocals of wavelengths from here to here. But for our purposes, for the most of the part, we don't actually need to worry about that, except to realize that what I'm showing you here is all wave numbers, and they're in inverse centimeters, 1 over the wavelength in centimeters. I'm showing you the wavelength. I'm showing you the wave numbers of in the infrared. They're just the low energy stuff is really low. The high energy stuff isn't actually that high. The other thing which is we're going to need to keep in mind, and which is quite beautiful, really, is that we know what the area under this curve must always be. The area under this curve is a constant times the temperature in kelvins to the 4th power. This is called the Stefan Boltzmann law, and it's a very important law. And I'm going to actually, never mind. I'm just going to go through it, bravely through it, and you have to go bravely through it with me. So here it is. Now, I said I was lying, but let me lie a little bit more. Every body radiates electromagnetic radiation. You are sitting there right now radiating electromagnetic radiation. I am radiating electromagnetic radiation. The radiation that comes off each of us is really determined by our temperature. This curve is for 260 kelvins. So that's actually minus 13 degrees Celsius. So that's kind of a cold body. But if I change the temperature, one thing that happens quite briskly is the area under the curve is always sigma t to the 4th. If I change the temperature by 10%, the area under the curve goes up by 40%. The shape of the curve doesn't change much, but the whole curve moves up and gets a bigger area under it, and the peak moves over a little bit. So we are radiating in the infrared, about 20 microns. Oh, I can do a demo. I got something here. See, look at this. Boom. Well, 35 Celsius. That's 308 kelvins. 308 kelvins, that, you know, that means I'm radiating somewhere, I don't know, 10 microns, 20 microns, something around there. The peak of my radiation is going to be about there. That's right. And, you know, that's how a certain class of night vision optics works. Some are image intensifiers and they use optical light and amplify it, but there are others that just will detect you moving across a field of battle because you radiate and you can't help it. So that's important stuff. And there's more to say. Oh yeah, oh yeah. Whoops. So now I want to look at something kind of similar. I'm looking at the top of the Earth's atmosphere. And I'm going to look at the radiations that are coming in from the sun. They haven't gone through the Earth's atmosphere yet. They're up there at the top. And I'm going to plot the flux in watts per meter squared here. And I'm plotting them against wave number here. Now, if you notice, the number that I had about here on the previous graph was 500 wave numbers. Here I'm at 10,000 wave numbers. That means I'm dealing with electromagnetic radiation that has 20 times the frequency. This is in fact the visible. 10,000 wave numbers in this region is the visible light. And that's not surprising. I mean, this is the sun radiation coming into the earth. And you can see though, it doesn't look nice and smooth the way the one I showed you on the previous slide looks. And you can see there's all kinds of jaggles and jiggles and joggles here. They're very sharp. That's because the sun has an atmosphere. That is, the light from the sun doesn't come from down in the deep part. Down in the deep part, the temperatures are many millions of degrees. The light comes from the sort of outer surface. That's what we can see. That's called the photosphere, because it's where the light comes from. You know, we have clever people all the time. But above the photosphere, there's still some solar atmosphere. So the main body of light comes through that atmosphere. The sun's atmosphere has stuff in it like hydrogen gas, and hydrogen gas will absorb the light so that suddenly light that's coming from the photosphere cannot make it through. So you see all these very sharp dips in the curve are understood as arising from traces of calcium, traces of sodium, traces of stuff in the atmosphere of the sun. So the energy can't come straight out of the photosphere. It comes, some of it, out of the sun. Well, how much like a black body is this? And so I can lay this over here. Things get a little vague, but you can see here this nice smooth curve. This is the same kind of curve that we saw on the previous slide, but this one has a temperature of 5,800 kelvins. The one before was 260 Kelvin. They're kind of Earth-like.
Are you ready to have a call?
Yeah. All right, I have to deal with a small interruption here. All right, so you see the smooth curve. Scram. Okay. Anyway, small black body, or definite similarity. That's what I want you to see, is the similarity. But I want you to see something which is kind of interesting. You notice, yeah, I've matched the peaks pretty well. The black body curve is giving me the peak radiation where I'm observing it in our visible, pretty much. But I'm getting more energy out here than can come from the black body curve. So how do you explain that? And the reason I want to explain it is because we're going to use a similar explanation when we get to talking about similar curves for Earth, and probably not so much Venus, but you'll see. The way you explain it is you say, oh, I get it. there's radiation coming from deeper down in the sun. There's radiation coming from a hotter part of the sun that can make it through the atmosphere and come out. And there's radiation that from at wave numbers that can't make it through. So an atmosphere begins to do some filtration. An atmosphere will be emitting from the top of the atmosphere by itself. It will be radiating. It's a hot body, but it may be transparent to radiations that are coming from deeper down, and those will be coming from a hotter part of the sun. And so that's why you can get energy coming above the black body curve that I've used, that I've kind of fit to the actual solar radiation. Is that everybody see what I'm trying to argue here? It's an important argument. Anyway, you're seeing two things that we're going to see again. You end up with the actual spectral radiance, as it's called, the curve we're talking about. You end up with the actual spectral radiance is a composition of radiations that are black body, but from different levels. And so they're coming from slightly different temperatures. And then they produce what you actually see. But we still end up using the black body radiation curve to understand what's going on. And that's part of its use. And so here we've been seeing the effects of the sun's atmosphere on its radiation. All right. Now I want to do a classic. I want to use black body radiation to determine what we call the black body temperature of Earth. And this is an artifact. I mean, this is a kind of fictional artifact that's useful for thinking about these things. It is the temperature the Earth would have if it had no atmosphere and was in thermal equilibrium with the sun. In other words, the sun's radiation comes into the Earth, and you see it here coming in, solar constant, S sub C, 1364 watts per meter squared. We know that number. We can measure it. We measure it often. And we're going to find out what must be the temperature of the sphere of the Earth in order to radiate out as much energy as it receives. So it's got 1364 watts per meter squared coming in. Well, first of all, the 1364 watts per meter squared does not distribute itself evenly across the surface of the sphere, because the sphere is bent. But we can get around that, because what we can see is that the Earth is intercepting what's coming in with a cross-sectional area of pi r squared. So you see the bright side of the Earth is cut by a diametral circle with an area of pi times the radius of the circle squared. And that's how much energy it can collect from the sun in a second, let's say. And of course it rotates, and so this is going on all day. In other words, it rotates and it all gets averaged over the whole Earth. And then the Earth gets rid of its energy. And again, this is an artifactual assumption maybe. We say the Earth is this ball. The surface area of the ball is 4 pi r squared. And so what's going to happen is the Earth is going to, spherical area of 4 pi r squared is going to radiate energy away. Well, it's going to radiate it away at sigma times t to the 4th. That's your Boltzmann law. If something has a temperature of T, it radiates at sigma t to the 4th watts per square meter from every square meter on the surface. And there are 4 pi r squared of those. And so what you got for equilibrium is the sigma t to the 4th times the 4 pi r squared has to equal the 1364 times the pi r squared. Well, that's very nice, because the pi r squareds cancel. And so sigma t to the 4th is just equal to 1364 over 4. And I know what sigma is. I wrote it down somewhere already. It's 5.68 times 10 to the minus 8 watts per meter Kelvin fourth, something anyway. I know what it is. I can solve the equation. I can tell you what T has to be in order for the 4 pi r squared of the Earth to radiate away what's coming in from the sun. And it's 279 Kelvin. Not bad. 6 degrees Celsius. It'll be a cold planet. We think we're at about 15, but 279, reasonable Earth size. And as I say, artifactual. Well, it's artifactual in one other particular way, and that is not all the oncoming radiation is absorbed. This is an important correction. Only 30% is, only 70% is absorbed. 30% is reflected off the planet, off the deserts, off the ocean, off the clouds, off the ice and the snow, the polar caps, off Greenland. Those are particularly good reflectors. But on the average, over the whole planet, 70% gets radiated away. So it isn't that I should put 1364 in here. It's that I should put 955 in here. And when I put that in there, I get T equal 255. And that's a number you'll see people quote all the time. That is the black body temperature of the Earth in equilibrium with the sun without an atmosphere, without greenhouse effect, without global warming, without anything. In other words, we would freeze our butts off if it were not for the atmosphere. Now, I can do exactly the same thing. Snowball Earth is what we would have at 255 Kelvin. I mean, 255 Kelvin is minus 18 degrees Celsius on the average. Okay, do the same thing. I'm going to be faster this time. I'm going to do the same thing for Venus. Venus cross-section, so forth. Spherical area, 4 pi r squared. Bigger solar constant coming in. Venus temperature rise. 328 Kelvin is what you get for Venus if you don't correct for the reflected light. But it's not all incoming. It's 80% reflected. 526 watts per meter squared. You get 220K. The black body of temperature of Venus with the same albedo that it has with an atmosphere, little swindling there, is colder than Earth. But that's not really relevant, okay? But I want you to see what a black body temperature means when you talk about a planet's black body temperature. So that's it. Snowball Venus. The actual temperature of Venus is 743 Kelvin. Now, this is kind of physics at work, our physicist's mind at work. We've done this calculation with this model that we knew was wrong all the way through. But we know it's very basic. And when we come through with a discrepancy as bad as this, when we say that the basic model says 220 and we're actually seeing 743, we know there's something else to look for. And that, of course, is the point here, is that we got to talk about the atmospheres. We have to understand what an atmosphere does that makes such a huge difference. All right, just kind of a pause in the activities here for a moment. Here's kind of where we're coming in. This is what we think Earth's energy budget actually is. People have measured and measured and measured and calculated and tried to figure out what's going on. So you see this number 341 here? That's 1/4 of 1364. That 1364 watts per square meter that comes in from the sun, we said on the average delivers 341. So we're dealing with some kind of global averages here. So 341 watts per square meter comes in. 79 watts per square meter gets reflected from the clouds. 23 gets reflected from here. So 102 gets reflected there. That's your 30% reflection. If you do 30% of 341, you'll see 102 watts going out. So we're doing a really detailed budget here. The result is only 161 watts per square meter are going to get absorbed on the average. If you're uneasy, I mean, to make you uneasy, think about what the average means. You know, this is not what's coming in at the North Pole right now. This is not what's coming in at the South Pole right now. It's not what's coming in. Much more is coming in at the equator than is coming in at either pole, and less than the equator, more than the North Pole and less than the equator is coming in at mid-latitude. So this 161 is kind of smoothed out over all that. That's what we're doing. But okay, it's still got to be there to get a balance. Well, what happens? How do we get 161 off the planet? That's what our job is. If we can't get 161 off, we're going to end up getting hotter and hotter until we have enough temperature to get 161 off. That's what goes on. But we have to do better than that, because not only does 161 get absorbed by the surface, the atmosphere actually absorbs some of the incoming. All right. So here we have 239 coming in, absorbed by the atmosphere, absorbed by the planet's surface. Then we have to move some stuff off the Earth. I'm going to kind of skip over this, but we move stuff off, heat off the Earth by condensation of water. Very good. So you have water vapor evaporate, and then you have it turn to water and rain. But the heat stays up in the atmosphere. And so you've moved 80. But here's the interesting one. Here's what's going on. That's really a big one. There's a layer, the atmosphere absorbs heat and heats up. It heats up to the point where it sends 339 back down, 333 down to the Earth. And then the Earth has to send some of that back. Somehow or other, this has all got to get back out into space. So the Earth takes the 333, adds it to the difference between these three numbers. That you don't have to follow that. Anyway, the result is there's an exchange of heat back and forth between the atmosphere and the Earth, which heats the Earth to a temperature sufficient to send out. Some of it can just go straight through without being reabsorbed, but it tries to send this out and it gets reabsorbed. And so it keeps getting cycled around and around until the atmosphere gets hot enough to emit 169 watts per square meter from the atmosphere, which added up makes the 239 that we said we were going to have to get to make the 78 plus 161. That's the Earth's energy budget. That's what we depend on the greenhouse effect to maintain that budget. These guys who are doing this, Trenberth and company and his colleagues, actually are saying down here something which I don't quite believe, but, well, I believe it, but I don't know that they proved it. They're saying net absorbed, 0.9 watts per square meter. So all of this juggling of numbers, they say you end up with 0.9 watts per square meter going into the Earth. That's global warming. There's a net inflow of heat. You can see a couple things here. Global warming can be achieved by rather delicate changes. I mean, these are fairly good sized numbers. And in the end, we're worried about the difference of the order of 1 watt per square meter. Okay. So that's our kind of story of global warming. Now, what has that got to do with atmosphere? I want to go back to a picture which is kind of like the one I showed you before of solar radiation. Only this is different. I was showing you the solar radiation at the top of our atmosphere coming in. This is Earth's radiation at the top of our atmosphere as detected by a satellite. When I first saw this, I thought, I don't believe this. I mean, this can't be right. And I said, I don't believe it because here's the black jiggly curve is the radiation. It only goes down to 400 wave numbers because it was taken with a satellite. The satellite only had the capability of looking to 400. I mean, this is the range of detection. And it's a long time ago. This is 1970 data. So really, but I looked at it and then you see someone has thoughtfully put on black body curves for different temperatures, 200 Kelvin, 240, 280, and then 320. So it looks as though if we think back to what we were seeing before, it looks as though this is coming from some complicated thing going on between 260 and 270 Kelvin. This looks like it's going from something maybe around 220 Kelvin. These things are going out here at sort of, again, 240, 250, 260. But these seem to be coming from something at 320 Kelvin. And I was saying to myself, where on earth are you going to be 320 Kelvin? Then I looked up and, oh, I don't have it here. Too bad. No, all right. But I looked up on, I went and looked up the original paper from which I had got this graph. Oh, you know what it said? It said, this satellite, this is taken at 12 noon GMT, and it gave the latitude and longitude, and we were directly over the Sahara Desert. And we were looking right down at 320 Kelvin on the surface of the sand of the Sahara Desert. No clouds, nothing in between us and that. 320 Kelvin is actually quite a reasonable number. But the point I want you to appreciate here is, once again, we see how the actual radiation comes from different places. It looks as though the CO2, so then I got to talk a little bit about absorptions. And that, of course, is the point. Here we have, we said, you know, why isn't it, no, let me back up one other thing. I showed you how the area under each of these curves goes as the fourth power of the temperature to which the curve corresponds. But the other point is that the area under the curve tells you the total amount of energy being radiated summed over all the frequencies at which radiation is occurring. So if this is an actual curve of radiation coming from the Earth, the total amount of radiation is the area under the curve. Now, here again, it gets a little, yeah. So is there a black body curve that will have the same area under it as this curve does? Well, sure there is. I could find it, and I would say, oh, well, that would be how a black body would radiate. However, that actually doesn't make sense, because now we're talking about such detailed data. This is no longer average data. This is data from March. No, this is data from, I think, August 1970, Sahara Desert. And there's no equilibrium between the ingoing radiation of the sun and the outgoing radiation from the Earth. Not at that latitude, not at that season of the year. We're counting on heat being moved from there north and radiated away somewhere else on the Earth to maintain the equilibrium. So there's got to be some atmospheric processes. Still, what I want you to understand is these radiations are coming from someplace cold. These radiations seem to be coming from someplace cold. These radiations seem to be coming from someplace hot. We're into the question of the structure of the atmosphere. But I think I need to skip this slide because it's too complicated. What I need to do, and I think I will. What the slide was intended to show you is some details of how CO2 absorbs infrared radiation. And what you do is you go into your laboratory and you stimulate the CO2 to emit. You radiate with a laser, you pulse it, you do something, you treat it badly, okay? And then it radiates. And then you study where the radiations come out. And this is a set of radiations which arise from rotational motion of a CO2 molecule, all these little red jagged things, all the way up to here, which is a peak of absorption of the CO2 molecule. And this is what produces absorption right around 667 wave numbers. You see where the dip is occurring here in the emission of the radiation, right around 667 wave numbers. That dip is the beginning of the greenhouse effect from CO2. These are dips also which arise from water vapor. CO2, this is a dip due to ozone. We don't hear much about ozone and greenhouse effect, but ozone absorbs energy. Turns out ozone also blocks UV light, which turns out to be useful to us.
It's really nice to see a professor who has good handwriting.
Well, I like this guy a lot, and he's a skeptic. When you get all done, he's not so sure what's going on. And I think he's wrong for reasons that I'll talk about after a while. But his name is Michael Van Biezen. He has 61 approximately 5-minute episodes on YouTube of video talking about the atmosphere and how it absorbs heat and how it generates the greenhouse effect. Well, this is probably not a bad point to stop, because we have now established that it's these molecules that are absorbing. This is an important effect that Van Biezen is talking about, that you have to have the fact we have a very small amount of CO2, but it's in a matrix of an atmosphere of other gases, and that is enough density and enough collisions so that the ability of the CO2 to absorb is enlarged a lot, so-called pressure broadening. Pressure broadening is clearly going to be important in Venus, and we've established that there is a greenhouse effect, and that these gases feed that, exhibit that, they create that greenhouse effect. What I want to do, I'm going to stop about now, but what needs to be done next is to examine how that integrates into the atmosphere. The atmosphere has structure, has a thermal structure. It has we talk about the troposphere, we talk about the tropopause, we talk about the stratosphere. So we have these layers of our atmosphere. There's temperature variation through them. All these things are important in the greenhouse effect. But the really important fact is that if you begin to study how the CO2 works, and you imagine it as in layers, that is to say, you imagine a layer of CO2 sitting above the surface of the Earth, that layer will get heated to some temperature. It will radiate back down to the Earth. It will radiate into the layer next above it, which will absorb the radiations. So if you imagine stacking these layers one on the other, you begin to get a kind of picture of a mechanism for absorption that isn't such a greenhouse effect so much as piling on blankets. And you put one blanket over you and you're warm. You put 2 blankets over you and you'll be warmer. And you put more blankets over you and you may be too hot. And this is where the issue comes for certain class of skeptics. They say, oh, the CO2 is too small to do any damage. You add some more CO2, don't worry about it. But I think what we want to be able to see in order to deal with that question is something I'm going to have to leave for another time. But for now, what you see is that, and then we'll come back and we'll use some of these ideas that I've already talked about, the black body radiation, how the radiation occurs from different layers below the top of the atmosphere, and how that achieves thermal equilibrium, a balance between what's coming in and what's going out. Well, I'll stop there. Maybe I could spend some time answering some of these questions that I see there are so many of here in the chat.
Quick question, Charlie.
Yeah, go ahead, Dick.
You talked about the idealized re-radiation of the radiation from the sun, from the Earth. Does that take into account the radiation has been absorbed by various materials and then re-emitted at a different temperature?
That's absolutely what's happening.
Being absorbed.
So what happens, of course, is you absorb radiation, and that raises your temperature. That's in that simple model that I was showing you. We have the energy coming in, and if you're going to, and you will go to an equilibrium where the temperature rises to a point where the Earth is emitting as much energy as it's receiving.
Well, but some of that energy gets absorbed by materials and converted chemically, for example, to other materials.
Yeah.
But yet some is still hot, so that's going to radiate at a different wavelength, usually a little bit lower.
Okay.
Our energy, I mean.
Yeah, I mean, you're right. The energy can be parceled out in all kinds of different ways, but if it's going to stay as heat energy and not get locked up in some way, in some other form of energy, if it's going to stay as heat energy, you're going to get to a temperature where your heat going out is equal to your heat coming in.
Yeah, what I'm asking is those numbers that you gave us.
Which ones? Without atmosphere or
both?
Okay.
Both, with and without, but I'm talking about.
Yeah. So you're talking about the Trenberth energy budget, really?
Yeah.
Let me see if I can get that. I'm not sure. Let's see.
Because what I'm really asking is that does that take into account energy from the sun that's absorbed by the Earth and transformed into other forms of energy, let's call it?
I think
not re-emitted.
Yeah. Well, I think in a sense it does, Dick, because you see over here. Let's see. I should share my screen again, or I should share my screen. Here we go. All right. So,
yeah.
Okay. So you see over here the net absorbed 0.9 watts per meter squared.
Mm-hmm.
That could be going into the other forms. That doesn't necessarily mean that it is raising the temperature.
Okay, so this comes from actual measurements,
rather. Well, they claim that, but I do not believe it. When you get down to this level of refinement, I find it hard to believe that they have that kind of precision.
You and I are on the same wavelength, then, so to speak.
Yeah, but you're right. There, you can lock some up, and that would mean that it wouldn't go to raising the temperature. But you can't go on doing that.
Yeah.
Indefinitely.
Agreed.
Okay.
Charlie, do you know what the average world energy consumption amounts to wattage per meter square that we inject into the soup?
Yes, that's known. I've actually got it. I mean, I could leaf through my notebook here and I'd find it. I think it's 150,000 terawatt hours per year of energy. And then you have to, all of these guys, they have about 7 different units that mean the same thing.
Okay.
But anyway,
I'll make the conversion. Okay, thanks.
Okay, anyway, I think it's 150,000 terawatt hours. And I used that to calculate how much CO2 we were putting into the atmosphere, because you know that when you burn fuel, you get a certain amount of energy per CO2 molecule. So you just take the total energy you consumed and divide by the energy per molecule. You get the number of molecules. And it was something like 10 gigatons of carbon added to the atmosphere per year by us, a very noticeable amount.
That assumes all the energy going into the atmosphere is a byproduct of some sort of combustion that produces CO2, correct?
Yes, it does, but there's a lot of, it assumes also some kinds of efficiencies. And so, in fact, it's only about 70% of the total energy consumption that's coming from combustion of fuels, and most of it from oil and natural gas. But the energy, there's that 150, if I've got the number right, if it's not 150 million, I think it's 150,000 terawatt hours. I think that also does not include the energy used producing it. in other words, it is not telling you the true inefficiency of what you're doing. And I think the two things will pretty much wash. So that
Yeah, it's interesting. It's crazy math.
And furthermore, if you come off, if it's going to turn out to be 9 gigatons instead of 11, who cares? These numbers are all kind of 10% numbers. You just
Once you fall off the cliff, it doesn't make any difference how tall it is.
well, it sure does if it's a foot.
That's right. It's not the long fall, it's the sudden stop.
Okay. All right. Let's see. I'm not supposed to say, if I don't vote, I can't complain. Oh, that's back to John. I'm looking at the chat now. Could I include Mars since it's so different? Well, I will give you a little bit of Mars at the end. Do we believe there are no other chemical elements than we have on Earth? We certainly believe that, Harry. We think we know all there is to know about elements. Well, that's not quite true, but we know that they're moving. Not all meteoroids, asteroids are in the asteroid belt. Yeah. Carl Lazarus, absolutely right. Solar irradiance follows an inverse square law with distance from the sun. We use that fact. That's how we know how much energy the sun emits. We measure what falls on 1 square meter above the Earth and then work that back.